Let's say we have random variables x and y that are the deterministic functions of one another, such that y equals g of x, where g is invertible, continuous, and differentiable transformation. The common mistake here is to assume that the equality displayed on the slide is true. Let's now consider an example that shows for this to be a wrong assumption. Let's say y equals x divided by 2, and x is uniformly distributed from 0 to 1. You can see the red plot, which corresponds to the PDF of x. Let's now consider the incorrect assumption described earlier. If we believe for it to be true, then the PDF of y would have to be 0 everywhere, except for from 0 to 0.5, and within this interval, it would have to equal the x's PDF. You can see the corresponding plot in green. The flaw of this assumption should now be evident. The area under the curve for the y's PDF would be equal to 0.5, but this violates the definition of PDF. Let's now see how we can fix this problem. When random variables are the deterministic functions of one another, the following property must be preserved. From here, we can solve for the PDF of x, and see how these distributions really relate to each other. Let's now go back to our example, and find the actual PDF for y. The problem statement gives us that the g of x is x over 2. We can then find that its partial derivative is equal to 1 over 2. If we now substitute everything we know into the formula we derived earlier, we will find the actual relation between the functions. Let's now observe the plots of these functions, and make sure that they satisfy the definition of PDF. We can see that the PDF of y equals 2 in the interval from 0 to 0.5, and 0 elsewhere. The area under this curve is 1, so now the conditions of the PDF are satisfied. If we were to work with random variables of higher dimension than a scalar, we would use the formula on the right.